Okay, so let's talk about another method to solve differential equations. Sort of two methods, but they're kind of the same. Substitution and exact differential equations. So the general idea for substitution is that it's what it sounds like. It's like letting u be something, or in this case we're going to use the letter v. But v is going to be some function of x and y, and we get to decide what that is. And different situations, it's a good idea to do different things. But whatever it is, we're going to introduce it and then try to eliminate one of the original two variables. So that way we'll be left with v and either x or y, whichever one we don't eliminate. So an important type of substitution is when you have a homogeneous differential equation, which is one that has the form, if you can write it this way, dy over dx is a function of y over x. So if you happen to have such a thing, we substitute this v. So like I said, v can be any function of x or y. In general, it could be whatever, but in this case, it's going to be y over x. And so just to walk you through how this works, we're going to substitute this and rewrite this differential equation. So let's figure out dy over dx. Well, v is y over x, so if I solve for y, I get y equals v times x, and then I take the derivative of both sides, and so dy over dx is, okay, here I've got the product rule. So v times the derivative of x, which is just 1, plus x times the derivative of v, which is this. So that's my y prime, or my dy over dx. And so I substitute that up here. So I get this. So I've rewritten that here. I wrote v prime instead of dv over dx. So I get this equals f of y over x, and y over x is v, so that's f of v. And we have eliminated y. This new differential equation only has x's and v's. And by the way, this new differential equation is going to be separable, and we know how to solve separable differential equations from before. So in general, what you do is you solve this one. Like I said, it's separable, and then you take whatever answer you get. You're going to get an equation involving x and v, and then just replace all your v's with y over x, and then you're done. Let's do an example. So here's a differential equation, and first of all, it may not be obvious that this is homogeneous. Let's solve for y prime. So I'm dividing everything by 2xy. So when I divide this by 2xy, I'm going to cancel an x over 2y. When I divide this by 2xy, I guess the 2 cancels and the y cancels, so I get y over x. And this is a little bit silly, but just to really drive it home, the original description was that y prime is a function of y over x, and here I've literally written this as a function of y over x. In other words, everywhere I see either letter, a y or an x, it's as a fraction, y over x. So yeah, of course, this is going to end up being, getting a little bit ahead of myself, but of course, we're going to make that substitution. V is y over x, and so this is going to be 1 over 2v plus v. But yeah, like I said, I got a little bit ahead of myself. Let me keep doing this substitution. So what does this turn into? This turns into, because y prime is v plus xv prime, so let me rewrite this here. Y prime is v plus xv prime, and we just wrote that equals this. So now we have my differential equation with just v's and x's. And get a piece of paper here. This should be separable, like we were saying. So I guess I just cancel a v. So, right. We are going to separate the variable. So let me start writing dv over dx. Because how does this go? We want to get all the x's on one side with the dx and all the v's on the other side with the dv. So let me rearrange things here. I'll get 2v dv, and then I need to move my dx to the right, and I'll divide by x. Something like that. Okay. The variables are separated, so I integrate both sides. V squared equals natural log absolute value of x. This is where I should start writing plus c on one side. And so we don't have an initial condition, so we're not going to be able to figure out c. This is basically our answer, except we have to remember what we made, that we made this substitution, and we want to put the final answer in terms of the original variables. So v is y over x, so this is y squared over x squared equals like this. And I could try to solve for y. I mean, it's not, well, I would have to have a plus or minus in my answer, of course, because I'd have to do a square root. Let's not solve for y. I think the answer in the back of the book says this. They don't all solve for y all the way. They don't take the square root, so I think that looks nicer. Okay, anyway. Let's talk about exact differential equations. So here's the theory of what it is. This is about the level curves of a function of two variables. So if you remember from Calc 3, if I have a function f of xy, I can look at the 3D shape, like the graph of this function z equals f of xy, and that's like a 3D shape. And the level curves are like the horizontal slices of that 3D graph. In other words, you take a slice a slice parallel to the xy plane, and that gives you a curve in 2 dimensions. And one thing that we learn in Calc 3 is that the level curves are orthogonal to the gradient. That's one of the cool things that the gradient of a function does. Gradient is this vector you make out of the partial derivatives. So here I drew a picture. We're imagining that this is the level curve of some function f of xy. That's this curve. And what I just told you is the gradient. So I drew this vector, this is the gradient of f, is orthogonal, so makes a right angle with the tangent line. And I'm going to express a tangent line using the vector 1 comma y prime. I mean, that has the correct slope, right? The slope is supposed to be y prime. So if I divide this by this, I get y prime. So what we're saying is these things are orthogonal. And so what does that mean? Their dot product should be 0. So I take their dot product. And so that's this times this plus this times this, and that's here. And because it's supposed to be orthogonal, the dot product should be 0. So this should be 0. What I just wrote is the form of an exact differential equation. An exact differential equation is a differential equation that you would get by taking a function of two variables and writing down this equation for the tangent lines of its level curves, like we just talked about, and you get this. Of course, y prime, we often go back and forth between writing y prime or dy over dx. So if I wrote dy over dx here and then multiplied everything by dx, then there would be a dx that ends up here and a dy that ends up here, and you would get this. So you often see it this way. Okay, so what we have to do is we have to learn how to do that backwards. We have to we have to learn how to get something that looks like either one of these, and then figure out what the function f is, because the solution to this differential equation is going to be a level curve of this function f, whatever this function f is. So it's all about going from this to finding your function f. Of course, not every differential equation is exact. Not every differential equation has this form. So you can't, just approach it as if you're definitely going to find an appropriate function f, because you're not always going to find an appropriate function f. So let's talk about that a little bit. How can you tell if a differential equation is exact? Because you're just going to get, there's going to be some function m which might depend on x and or y, and then similarly another function n, and you're just going to get this times dx plus this times dy equals 0. And then how do you tell if it's exact? In other words, how do you tell that there is a function f such that m can be matched up with the partial derivative with respect to x, and n can get matched up with the partial derivative with respect to y? Well, remember, and this is another fact from Calc 3, and this is a little bit technical, I'm going to sweep the technicalities under the rug. Under nice conditions, and when I say nice, I mean that there's something about the partial derivatives being continuous nearby the point. That's what I mean by nice, so I'm not going to say much more, I'm not going to say anything more than that about it. These conditions are satisfied in reasonable situations that you would be talking about in real life. So under nice conditions, the mixed partial derivatives are the same. In other words, if I take my function f and I do the mixed partial derivatives, meaning I can do the partial derivative with respect to x and then do the partial derivative of that with respect to y. So it's like a second derivative that I'm doing with respect to x and then y. Under nice conditions, I would get the same answer as if I did the partial with respect to y and then x. In other words, it doesn't matter what order I do the partial derivatives in. If I'm going to do one derivative with respect to x and one with respect to y, it doesn't matter what order I go in. In other words, if m is supposed to already be the partial with respect to x, and I do the partial of that with respect to y, that's one way of getting that's one way of getting this, the mixed partial derivative of f. And I should get the same answer as if I took the derivative of f with respect to y, which is n, and then did the derivative of that with respect to x, because the order shouldn't matter. So under nice conditions, one check that you can give if you have a differential equation that you suspect may or may not be exact is to just check whether this partial derivative with respect to y of m equals this other partial derivative. However, in practice, I don't really do this unless the instructions of a problem specifically say I'm supposed to do this. I don't really check. What do? I just approach it by trying to find my function f, and if I succeed, then it was exact. And if I have trouble, then I start to suspect that it's not exact. And usually at that point, I don't feel the need to test whether it's exact. Once I know I'm running into trouble, I know I have to try something else. So I start checking, maybe it's first order linear or one of the other techniques that we learned. So how does this go in practice? We get something that looks like this, and like I said, we sort of wrote it in this form. I've got some function m, so it's like this is my m, and some other function n, so this is my n. So what do I mean by trying to find f? Well, if the appropriate f exists, meaning that this is exact with this function f, then Well, this is supposed to be, let me get this back here. This is supposed to be the partial with respect to x. And the dy part is supposed to be the partial with respect to y. So let's use that. So let me be careful how I say this. F has the following form. I'm going to take an antiderivative of this with respect to x. So how does this go? This is like Calc 3 stuff. I treat y as a constant because this is an antiderivative with respect to x. So 6xy, I'm just, so the 6 and the y are going to carry right through here. Let me write something a little bit silly. I could do more than this in my head, but the 6 and the y carry right through, and x turns into x squared over 2 because that's how antiderivatives go. The y cubed, that whole thing is just a constant. How do I do the antiderivative of a constant? Well, this is an antiderivative with respect to x, so I'm just going to stick an x on there. And normally when I do an antiderivative, I write like plus c at the end or plus a constant at the end. This is a multivariable situation, so what I'm going to write is, well, it's like a constant, quote unquote, but it's only constant with respect to x. In other words, it could depend on anything else, and the other important thing it could depend on is y. So let me, here, it's like a constant, but only constant in the sense that it doesn't depend on x. It might depend on y, so I write it as like a function of just y. And okay, yeah, maybe I should have canceled these as I went, but all right, so we do that. So that was just using this, but I can also use this. So f should also be, if I do the antiderivative of this with respect to y, that's another way I can get information about f. So let me try to be faster. So this is an antiderivative with respect to y. We're keeping x as a constant. This turns into 2y squared. The whole thing is a constant, so 3x squared y. And for this, I'm like the y squared is going to turn into y cubed over 3, so I'll just write that because the 3 cancels. Plus a constant, and this just has to be constant with respect to y, so it might depend on x. So similar to this a of y, I have a b of x. So what I have here is sort of two pieces of information about f, and the miracle of exact differential equations is that these pieces of information don't contradict each other. In other words, any part that depends on both x and y should be in common. So I have a 3x squared y, and I've got a 3x squared y here. And here's another part that depends on both x and y. I've got a minus xy cubed here, and sure enough, a minus xy cubed here. This part down here also has something that doesn't depend on both x and y. It has some part that depends only on y. So that's telling us what this mystery function of y here is. Like, we knew there could be something up here, as long as it only depends on y. There could be something up here that we didn't know what it was at the time. This is telling us what that was. At the end of the day, you just have to come up with a function f of xy that has this form and it has this form. So the quick way to do this is to just copy down the stuff that depends on both. So there's 3x squared y minus xy cubed. These are things that depend both on x and y, and they were here and they were here. And then anything else, I'm gonna copy down. It's possible, like in general, this one could have had something that depended only on x, and that would tell me what my b of x was. In this case, I guess I can just let b of x be 0. Like there could be a term here that depends only on x. In this case, there's not. There's one that depends only on y, but not one that depends only on x. Anyway, this function f it fits the bill. And at the end, the solution to this differential equation are the level curves of this function. And that level curve just means you set it equal to a constant. So 3x squared y, blah, 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 equals c. And as usual, this is a general solution, and it has some function c in it. We weren't given an initial condition, and if we were, we could find c, but we'll just leave it at that.